Welcome to EDU World Space.
In this question, we have a mass m distributed uniformly along a line of 2L, and a particle of mass m is at a point directly above the center of the line, a distance a away. And we are to calculate in this question the components perpendicular and parallel to the line of the force that is exerted on the little mass m. So with all of these types of questions, it's very important to start off with a picture. So let's go ahead and do that. So this will be our line of length 2L. So maybe this is the center, and then each of these is L. We've got our mass up here, and it's a distance A away from the line. Now, with these types of questions, generally speaking, what you want to do is consider just a tiny sliver of the line, dl, where we can try to figure out what is the force between this tiny little sliver of mass and the mass at the top here. So the force exerted by this tiny little sliver will be along this line here. And will be directed along that line. So this would be df. Now, to start to think about the direction that the overall force is going to be in, let's think about the fact that there is an identical piece of the line over here, dl, that is the same distance from the center of the line and will exert a force at the same angle in this direction. So knowing that each piece of the line will have this corresponding piece on the other side, this shows that the total force has a no component in the x direction. This is because, as you can see, the forces from these two pieces of the line will cancel each other out in the x direction and add in the y direction. So what we need to do here is focus on the y components. So let's consider what is going to be the force in the y direction from a little piece of the line dl. So we're going to use our regular expression for mass. For force. So gm dm, because we're considering a little piece of the line, and that's going to have a little piece of the total mass, dm. And then the distance divided by the distance between little m and dl, so that we're going to call r squared. And then to get the y component, we're going to notice this angle theta is the same as this angle inside the triangle over here, right? So of course we want to take the y component here and we're going to multiply by cos theta to pick that out. Now, this is no good as an expression to integrate over, which is what we want to do to find the total force, because we have a lot of different variables here. So we're going to try to work in terms of the variable L, because that will be very easy to integrate over, right? We can just integrate from minus L to L. So L equals 0 being the midpoint of the rod. So first of all, let's decompose what this dm is. So dm is going to be the linear charge density of the rod. We usually call that alpha times dl. So I'm going to substitute that in. Okay, and then I want to get rid of this r in favor of an L, and we can see from the triangle that cos theta, looking at this triangle here at the bottom, cos theta is going to be A divided by R. So cos theta is A divided by R, and R squared is going to be, if we're thinking about Pythagorean theorem, it's going to be A squared plus L squared. So this is A squared plus L squared. But R, we can also just write that as, instead of R, the square root of A squared plus L squared. And so in total, we get this new formula that is just in terms of the variable L. And this is really great because we can just go ahead and integrate this. So let's do that. We're going to go from L minus L to L. And we're adding up all the little pieces of the force, so that'll give us the total force. I'm going to leave everything that's a constant out in front and then just write down the variable parts of the integral here. So this integral can be a bit tricky. What I did is honestly just looked it up, what the antiderivative of this is, rather than go through a whole rigmarole of trying to find a special value or a special technique for solving this integral. So the antiderivative that I got is L over A squared times the square root of A squared plus L squared. Okay, and of course we are still evaluating between L minus L and L, big L. And so let's do that in the next step. So here we go. So L, summing in L, and then we've got A squared plus L squared to the 1/2. Minus minus, right? Minus minus when we substitute in the minus L. So minus minus becomes a plus. So we basically get the exact same thing for the second term here. So we can combine those two things together. That'll give us a factor of 2. So we got G m alpha times A times 2L all over what's on the bottom here. And that works out really nicely because lambda times 2L is the total mass of the rod. So we get GMM A. And actually that A cancels with one of the A's on the bottom. So let me leave that out. GMM A times A squared plus L squared. That's the total force from this line of mass on the little mass M. So that is the answer to the first part. And then in the second part, we've got a question about whether this result will reduce to the correct expression as A becomes very large. So what do they mean by correct expression? Basically, as A becomes very large, so you're getting farther and farther and farther away from the line, you kind of expect the line to start looking like a point charge because you're so far away from it. So what you expect is a GMM over A squared, right? The force between two masses, a distance A apart. So let's see if we get that. So let's consider A to be much, much larger than L. What's going to happen to our expression here? So if A is much, much larger than L, basically A squared plus L squared is just A squared. Adding a factor of L onto it is really not going to change much. And so what you get in the formula then is GMM over A times A squared to the 1/2, but that's of course just A. So A times A on the bottom gives you gmm over a squared. Okay, so that is what we expect for the force when A gets very, very large compared to L. Basically, it's just the force between 2 point charges a distance A away. So this is great. And that's it for this question.